This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
You get a good chance to talk to the people one-on-one. There's free beers put on by the club, so a bit of an incentive there. And the event's free as well, so yeah, come along after the lecture. See you there.
Okay. Last time, I got to this, talking about the function, just a generalised function, and I'm not going to read out all these words, just to indicate a, dare I say, systematic pathway to get to an outcome. Attributes, objectives, look for what's the free variable, that is the variable that is you can manipulate, play around with. Look for performance constraints, what's the most important, prioritise. Look for the inequality, as I've said, we're not looking for a number or a point on a chart, we're looking for greater than or less than. And up till now it's mostly been greater than, on the sort of like the upside of the line, but I'll show you an example in a sec where it's the other side, below. Substitute, for example, I had a lot of time when we had section area A as a variable that could be just removed from the process. We've got that functional requirements, geometric parameters, material properties, and from that we can get our overall function. Then we get our performance index, maximise, minimise, look at the charts. So that's, the least fun, but still important, the process, to remind you. But some case studies, which I think are a lot more fun, a lot more interesting. Springs. Springs store elastic energy. They release that elastic energy in a certain delta T, or, there's a certain time in which the spring can release that energy. And some texts talk about spring rate. Now, that's not the delta T. That's another word for spring constant, K, force divided by associated deflection. So that stored energy, how quickly the energy can be stored, how quickly the energy can be released. The very next topic is springs, and this idea about how quickly a spring can achieve that outcome becomes important for high speed equipment. And I'm particularly thinking about automotive engines and the valve springs in those automotive engines. And then we can ask ourselves, what materials make the best springs? And there's a whole heap of stuff up on the screen to just indicate a spring can be an axial spring, a leaf spring, an axial helical spring, etc. There's lots of variety. So let's just think about what's the maximum energy stored, and of course we might be thinking about per unit volume, we might be thinking about per unit mass. If it's volume and mass, if it's something that's got to act like a spring and go into space, for example. And this idea of uniformly stressed spring is important. Again, when I talk about helical springs, you'll find that the stress is not uniform across the thickness, which is okay most of the time. But if we're looking for minimum mass and we're not having a uniform stress across the section of the wire, well, are we optimising for mass? And the answer is no. But that's just something we'll either accept as not important or consider further. And sigma less than or equal to sigma f, i.e. we don't break, we don't exceed the failure strength. Now, those images up on the top right, I've got a friend, Shane Gooch, and over in New Zealand, he's my equivalent at Canterbury University, which is the university at Christchurch, New Zealand, where they had the tragedy of last Friday. And one of the interesting things is, that idea that gun laws have to be changed over there, if you're following the media. They also, it's part of a different culture to Australia in that they they seem to like being a bit more adventurous as a culture, as a country. That bungee jumping idea, New Zealand, the way the healthcare system works. If you bungee jump and hurt yourself, they'll still look after you. It's not as if being an idiot precludes you from going to hospital, which is rather interesting. Now, that's by way of introduction to these two images. Now, Shane had a spring-loaded, like we have Warman, the design and build and test competition, which is pretty, safe, and I like it that way. Shane had a job, a task, where students had to come up with devices that would fire golf balls as far as they could. And that meant creating a lot of stored energy. And you can see there's tubes, and I think that's a bungee type cable, and that one's got a great big coil spring inside it. And they'd have to, load up or introduce potential energy into that spring, and then, lock it in place with that stored energy in place, and then be able to release it in such a way that the release phase had a very, was impulsive. F delta T equals M delta V type stuff. So they could get maximum launch velocity, and they were on an oval, and balls went flying, and everyone had a lovely time, except those people that hurt themselves as the devices released their potential energy at the wrong time. Knuckles were grazed, cuts were introduced, etc. We're not going to do that problem. We're instead going to look at a bit of this Ashby stuff. Now, hopefully, while I was telling you about the photos, you've been having a bit of a look at all this stuff on the left. Strain energy per unit volume for a torsional or a leaf spring. Now, all this material can come from resources, books, the web now, of various kinds. And we get down with a lot of process that, for those who want to study for the exam, fill the gaps. There's plenty of stages here that I've cut away for the sake of expediency, compared to the very introduction to this material. Work out yourselves how to get to that point and how to get to that point. For low volume and low mass springs, where we've got our material index associated with sigma squared, and we've got the density there when we're thinking about mass. Once we're at that point, it's easy. There's heaps of, I'm not going to expect you to read it on the screen, but just to let you know that there are plenty of resources, plenty of guides to assist with this, especially when you go into something a bit more exotic. Now, here's that example I told you about. Young's modulus on the y-axis, strength on the x-axis, and you can see I've got some dotty arrows indicating that we're going downward, looking for a maximal. And on the left, I've got a list of candidate materials, so bottom left. Bottom right is a table that's pretty grey, I'm sorry, it's a scan. And the point that the table is later on, you can have a read, and it's got not just the material, but it's got a range of values for this material index for that material, and some commentary. So it's not just about trusting this material index and say, yep, that's what we're going to do. The comments help guide the engineer to what other parameters, what other features, what other performance issues are present associated with that particular candidate material. And we've started with ceramics. And there it is up there. Then we've got spring steel, which is in that little dashy line there. And then we've got titanium, which is, again, very close to the spring steel in this chart. Carbon fibre or carbon-filled reinforced polymer, glass fibre or filled reinforced polymer. Bit of just glass fibres are in that zone as well. Nylon down there, and rubber way down there. Now, not everyone did the Warman project with me, I know that, but for people who did and who were playing around with rubber bands, you would know that they're very, dare I say, soft or low stiffness. You can flex them a long way. You get your stored energy. You might also see that their strength, you might have, just as I was going through all those blue bounds, their strength is a lot lower than all the other materials as well. But another issue that, is it written up there? It's got written there, high loss factor. Now that's shorthand for you don't have to do too many cycles of a rubber band and its performance decreases dramatically. So it is not good for high reliability for large number of cycles. Yeah, and that's a very important, everyone who chose rubber bands for Warman would have learnt that, a valuable lesson. Same kind of deal. This time it's a new chart, specific modulus, that is E on rho, specific strength, sigma F on rho, that is we're thinking about with reference to mass. And we can go through the same essential process where we've got ceramics, spring steel and titanium joined. We've got the carbon and glass fibres up there. We've got our nylon up the top and our elastomer or rubbers down the bottom. So they're all in the same kind of relative zone to a degree. But again, you, the engineer, is able to systematically review various materials to check out how they perform. So that's, and then you go on and look at all the other things that you might like to think about with regard to the detailed design. New case study. A telescope mirror. Now, we're not worried, the actual mirror bit, the silver, is not what we're worried about. We're thinking about the material that supports that little bit of silver. Now, as of 1996, a long time ago now, it was a very, very big optical telescope, and it cost an awful lot of money because everything has to be precise. So let's just think about that number 200. It's 200 million. And of that 200 million, 200, the glass mirror cost about 10. So just one component was a very big proportion, 5% of the overall, build phase. So it's a lot. Here's part of the reason why. It's 5 metres in diameter, it's 1 metre thick, it weighs about 50 tonnes, so it's a big lump of glass. And it's interesting that when the engineers decided on glass, it's not as if light goes through the glass and then hits the mirror surface and comes back out again. The mirror's on the front surface. So the glass was used for its mechanical properties only. That is, not its optical properties, which is an interesting thing. And then, here we go, we've got a 50-tonne weight supporting about 30 grams of silver. So a very thin layer of silver to do the reflecting. So it's an interesting little engineering problem. And there's some photos of it. There's the photographer taking the photo of the mirror. There's the mirror up the back, and there's another human being or a human being up the front, sitting in that little tube. And there's when it gets cleaned before and after, to give you an idea about how readily these things can get dirty. All those images just off the web, everyone can see them. Here's something closer to what you've seen me do a few times now. And I'm going to go forward a slide quickly. Boom. That equation, just for an example, sourcing equations, deflection due to the self-weight at the centre of in this case, a great big disc. Simply supported around the outside is what we're asserting. It could have been fixed, but it's a metre thick. It's going to be hard to get an actual high degree of fixation if we're going that way. And also, they don't want it to deflect, so it's as thick as can be. Sorry, wrong way. But you might think, I'm just putting something to. I talk a lot about you've got to get it from here or there, get resources. Well, this, I should have put a red thing around it, but an example is Rorke's Formula for Stress and Strain by Warren Young. It's a book essentially filled with equations of the type you can see up there for various loading, various support modes of various shapes. And this is just an example where that equation would have come from perhaps something like this resource, and it's the top one. Just FYI, for future reference. So you don't just think, I just want you to not leave this lecture thinking, where the hell do all these equations come from? Well, some really smart person came up with them, and then we could just make use of them, which is great. So, what we're after is, blah, 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 we'll model it as a disk, we'll simply support it at its edge. It must not sag, and this is a cracker, it must not sag by more than a wavelength of light at its centre, under worst case, gravity-style loading, which is not much sag at all. No wonder it's so big. So its function, its objective, its constraints are provided, and it must not distort. So, another way of saying it, we want a high dimensional stability, plus we can talk about things like it mustn't change with temperature, it mustn't change with humidity, or it must change as little as possible with things like that. So, go through the process. What's its mass? What's its deflection? I've just told you where I've got a rough idea from that. Solving for thickness, T, we just rearrange. Talked about that. Do a bit more manipulation, and I'll let you do that in your own time, and we can get to this idea of mass, which is sort of what we're looking for, with respect to a whole heap of stuff. And we want to achieve that less than one wavelength, but we don't want to make it 100 tonnes when we don't have to. So we're still looking for the lightest possible mirror. And we want still with the greatest value of performance index, and all that stuff turns into that. Now, I hope that everyone can say, wow, that's a pretty big cutout of an awful lot of variables, and you'd be right. But all this stuff out the front, hopefully you can appreciate, the radius will be pretty much fixed, gravity is what it is, we've already been given the deflection, less than a wavelength, that's all okay, constant, irrespective of material of choice. You might be thinking, what about that power of 3 on 2? Where did it go? Well, this is a repeat of like a case study repeat of what people who went to the tutorials learning about CES would have been informed about. That you might remember that if we've got an equation of this type, we turn it into a linearized log equation, and we can rearrange and get just a simple y equals mx plus c type formulation depending on how we define our chart. That's why it's log, log, log type chart. Now for this one, that I've just, the power of 3 on 2, that carries over the whole of rho and e to the power of third, has no impact on the final material index investigation. And the reason being is, as per that little bit of mathematical or derivation, and all that it's adjusting is the c, the constant. Now that c has an impact on where a specific line might be. I could say, I could give you a number somewhere, I could define x, and then I'd just say, now draw me the line on the material selection curve with that information. And the power of 3 on 2 will have an impact, because it'll change its location. But that's it. Doesn't change the slope. So that's hopefully an interesting little insight from today's presentation. And on the screen now, with lots and lots of stuff that I'm, again, not going to read out, all the detail is there for you to review if you're interested later. We've got density versus Young's modulus, because after all, that's what we're looking at. And we want to maximise the ratio of the power of third on rho, so it's nice. We've got our plate formulation, which is nice to see. And up we go to this kind of zone, looking at candidate materials, and hopefully you can get a bit of a clue. Even wood is there. Glass is up there somewhere, beryllium's up there. Steels, aluminiums are a bit, lower, down the list a bit. the glass fibre or glass filled and carbon fibre, carbon filled, they're getting pretty close. So there are a few candidate materials in the zone. Zoom in a bit and have a table. And in this particular M1 line, glass, actually there it is there, glass actually on the line. And I'll just quickly, glass, steel, silicon carbide, glass-filled reinforced polymer, beryllium, foamed polystyrene of all things, and carbon fibre reinforced polymer. So some of the candidate materials. It's fortunate that glass is, given that this is like a reverse engineering problem, it's fortunate that they chose glass when they were designing that telescope, and that during using this little bit of analysis, glass is actually present in the list. Otherwise, we might have a bit of a problem. We'd be asking, why the hell did they choose it? Now, I did say that there's more to it than just the specific stiffness. Thermal expansion is important. Thermal conductivity is up there. And we've got, again, we can now cross-reference, and with CES, the software, it makes it a lot easier, but just for the here and now, the candidate materials can now be cross-checked with something like this. And again, I've highlighted beryllium and carbon fibre. Beryllium, it has lightweight, low alpha, just got to make sure I get this right, low thermal expansion. So you could say it's a good candidate. It's expensive, so it's light but expensive. So as written up there, it might be all right for a Hubble telescope, but maybe a bit too expensive for a Earth surface-based telescope. The carbon fibre reinforced polymer, light again, so we're looking for light, but has poor thermal distortion. So that sort of takes it out of contention a little bit. And this chart gives us a bit of a clue on that. So it's not as if we just have it, we're not having to remember qualitative information. This kind of approach reminds us of these kinds of informations, and then it allows us to project forward when you've got a new problem and someone says, oh, what about carbon fibre? And you might think, oh, I remember, I've got half a memory of this lecture where a few of these performance properties, and good, bad, up, down, not as good as, a bit better than, something else, these kinds of inequalities become apparent. And that's a more prettier, but still the same kind of chart. Thermal conductivity, thermal expansion. In this case, instead of having M2, where I've just got equals 1 equals a ratio, here we've got M3 equals an actual ratio of those two variables and gives us a thermal distortion. Get the same kind of outcomes. It's just, Ashby, in his wisdom, decided to change the way he would solve this particular case study. And again, same essential process. I'll just go back. Same essential process. It's just now we've got an M3 instead of an M2. So I'll stop at that point. So now I don't say here is the answer because the comments provide a bit more information that assists the executive decision making. This kind of case study does not just say, here is the answer to the tutorial problem, or here is the answer to the equation. It might be that you, the student, thinks, yeah, but I think that such and such other performance parameter is important. And then you'd go into another layer of investigation. So, and this one does, flywheels. I don't know how many of you are aware of this idea of having a rotating large mass in a shielded case, and that rotating mass can, it's regarded as a potential energy that can then be drawn on when needed. And people have played around with it as an energy storage and release device, and I think, there's if you want to have a look, Flybrid Systems. And I didn't check before this lecture, but last year that website was still valid. And this company was playing around with having a heavy rotating mass and a gear system so that rotational energy goes in, rotational energy comes out. And braking regenerative systems. Early on, when people were thinking, when we brake in an automobile, we're just creating heat through friction. Wouldn't it be nice if that braking process was actually, getting a wheel to spin faster, or actually use that energy in some positive stored way, such that then when we're accelerating off again, we can draw on that now potential energy. They had them in buses for a while, I know that much, but there's a reason why they haven't mainstreamed as much as, well, we might think. And I'll talk about that at the end of this little case study. As per everything else I've talked about in this topic, function, objectives, constraints and free variables, a list of stuff. We've got to have our sort of nice little image to give an idea of function. You guys are all penultimate year students, so everything on that slide should be familiar. You might not be saying, oh yeah, I understand everything and I can derive it all from first principles. But the idea of stress due to rotational activity, due to one bit of material wanting to fly away from another bit of material, I hope that that's all quite apparent. Angular velocity, thus stored kinetic energy, will be limited by the strength of the material. You don't want the whole flywheel to shatter into pieces. And I'll go back 2 slides. And rotational stored energy becomes translational or radial kinetic energy. Thus, this burst shield, to try and, if there is a risk of fracture and failure, the burst shield is expected to prevent that radial motion of bits to, travel beyond that shield itself. Okay. So we create our equations, and I've highlighted everything that's going on there. Energy, mass, must not fail, energy per mass, specific energy, and therefore we want to get down to a point where we want to maximise the kinetic energy per unit mass. Heap of stuff gets cancelled out, and we're down to something as simple as what we see on the screen. So after all that detail, which is still going to be used in the detailed design, you'll make selections, you will then find out the engineering properties of the material that is selected for the application at hand and go back through all this. But right now, for candidate materials, that's what we're looking at. We can also think about adequate toughness to resist this idea of fracture. And again, design for integration is where I actually teach you all a bit about fracture mechanics. Just enough to say that it's another very important material property associated with crack propagation when an object is under load, especially when it's under fatigue type loading or cyclic loading. You don't, crack grows a bit more, crack grows a bit more, crack grows a bit more, and then finally we get shatter. The idea is to try and predict this idea of this crack growth so that we can plan for it. Aerospace pretty much designs to fracture toughness. Okay, so we've got a performance. As far as we're concerned, it's just another engineering property with a certain upper limit for fracture toughness. And we've got our stored energy per unit volume at a constant velocity, so that's another nice little equation. Both R and speed are fixed, radius and speed are fixed, and so we'll be looking for the best material with something as simple as maximising density. So we're just cancelling out a whole heap of stuff. Energy per volume, density. So that's our, it's quite a simple measure. And then thus, this is very much analogous to my very early lecture when I talked about must float on water. This density one is again just a nice vertical line. That's M2, material index 2. M1 is as per up on the screen. Endurance limit, SE, which is nice, versus density, and we've got a set of candidate materials, which is rather nice. Now, that's not considering our fracture toughness. Our fracture, we must have a fracture toughness greater than 20, which is there. So everything above that line is important. And just for the sake of it, we can't afford to spend whatever we like, so we will say cost must be less than a certain amount. Price per kilogram, and it's just a start point. And thus we have another set of candidate materials. So the idea then, if we had CES, we'd be looking at one set and another set, get the intercept of those, which materials are actually our resulting candidate materials. And here's a way of doing it, just in a simple form. So we're looking at an overall zone, endurance limit per density, fracture toughness, and we've got some carbon fibre, glass fibre, titanium, magnesiums on the outside. So magnesium's out. Some steels are just sitting in that zone. Oh, no, sorry, wrong. Steels are outside the zone. We're getting an idea of what's available. Lead, nice big heavy stuff, out. I could say depleted uranium, which is a very heavy material. It might be in there for all I know if we did this properly, but this is where you, the creative engineer, might be thinking, what other materials are really heavy? And do they have an adequate fracture toughness, endurance strength to be able to be considered? Have I missed something? I just keep repeating, this stuff is not going to solve the problem for you, but it's a guide. It can help. So, for high strength, efficient flywheels, here's a heap of stuff. Here's the M1 value, given just a subset relevant to that last slide. And there's a range of numbers, and there's some comments. So composites come across as pretty damn good. Titanium less so, and then some steels, aluminiums, magnesiums are quite a way down, which is an interesting outcome, given what I was just saying about, don't we want heavy? Don't we want something that's nice and heavy, so when we get that, we don't have to have as much material rotating to have more potential energy. There's another way of thinking about this, and that is, what about low-speed flywheels? Low cost, and that cost factor before came into play. Toys, these, kids, essentially with friction of the wheel to the floor, will roll the vehicle along, and then through a gear system will spin up a flywheel that then the vehicle can be put on the ground, and it'll move some distance under its own energy. There's a little couple of little flywheel-based toys there. So function objective constraints are a little different. And this is where you'd say things like lead and cast steel or cast iron, the heavier stuff, that it's not going to spin to as high a velocity, and fracture or failure is not going to be catastrophic, because after all we're looking at smaller amounts of energy, because we're not strength limited, we're not velocity, it is velocity limited, not strength limited. You could go through the same essential process and get to that point. And there we are. There's our cast irons, there's our leads in that kind of zone. Alrighty, now why don't we have lots of, stored energy rotating flywheel devices in the marketplace? Energy density of alternative energy sources. Energy source, specific energy density, that is megajoules per kilogram, and some comments. So, as I've always said, springs, rubber bands, much less efficient method of energy storage than a flywheel. 0.01 in this indexing business I've talked about. A lead acid battery, it's large weight. That's why electric cars, lead acid batteries were never going to be a useful energy storage medium for electric cars. Lithium-ion batteries, they're probably getting better. This is back in 2010, we're 2019 now. So I think I might even have to change that, a little bit of slide. Obviously, lithium-ion batteries are doing well enough with efficient electric engines, etc., that Tesla and others are exploiting that. However, flywheels, they're in that, in this slide, they're in that same kind of zone, but they are not anywhere near the level of liquid petroleum gas, less than 1, and we jump to 46 for liquid petroleum gas, or 46 or thereabouts for petrol. So petrol tank, fill it up, that megajoule per kilogram ratio, we can use that stored energy in our petrol or diesel or whatever, and we can get it all a lot further because of the the storage to energy output ratio. So you can understand why, even now, petrol is king. It is so much more efficient. Now, again, I might have to look at... You guys can do it as well. Electric cars are on the rise. Something has happened to this particular row of this chart such that lithium-ion batteries have upped their efficiency, perhaps upped their specific energy density to a higher level, such that they are becoming more attractive. But flywheels are still where they were. And it's a lot of mess to cart about for this big ratio. And we're done. That is systematic material selection, just a nice little introductory lecture, series, to get you into the subject. Now bear with me while I pull up the next slide. Now, you might be happy to know that we're going to get into some maths and science, and it'll be pretty simple maths and science until you sort of pick up the complexities associated with dealing with reality. Now, I'm going to give you a bit of detail on coil helical springs. I'll be talking about some other spring modes as well. But I was joking before, you must all come for Peter McGowan's presentation. He and John Weir and then Philip Chen, it's just, they are such important bits of information that they share. So powerful for the student that's thinking, now what do I want to do as a job, and what will working as a real mechanical engineer be like? Those three people, when they come and present for you, will be really giving you some good, valuable advice. So I strongly recommend it. Pressure vessel design, I'll be going through it. Then John Weir is going to give you a case study that he worked on. It was a giant pressure vessel for Orica. Peter, tomorrow, is going to talk about the realities of material selection and the realities of being creative and then having, to be blunt, the management say, yeah, but, and then having to sort of work within the constraints that management might provide you with. So, but for now, for the next 15 odd minutes, mechanical springs. Now, this case is associated with torsion and bending. And by the by, the nuts and bolts on either side of this slide is just indicating, and anecdotally, the nuts and bolts of mechanical engineering, or if you like, the machine element design aspect of mechanical engineering design. It's the sort of stuff that books like Shigley is full of. That's what Shigley is doing for you, a whole book of machine element design. And I'm not going to cover the lot, just enough that I think that they're hitting a few beats that helps you extrapolate to the remainder of the book. No, I'm not going to get through all that today. There it is in bigger writing, but I'll make a start on some of the broad brushstrokes today. Now, as all things, before we called ourselves engineers, clever people were using the physical world to achieve outcomes that made life better. And up on the screen there, I'm sorry that's a rough drawing, but the idea of using a sapling or a very young tree, using its elastic properties to achieve something. This idea of a recursive bow, bow and arrow type bow, using the wood back then, using again its elastic material properties to be able to achieve an outcome. And of course, you might think, well, bow and arrow, so what? But there was before bow and arrow, and then there was after bow and arrow. Like a point in time where some creative person came up with this idea, developed it, and then, to be blunt, the group of people that had the bow and arrow, they beat the people that didn't when it came to, war and ownership of land and slaves and whatever else way back in prehistory. So there's always that step change. At least in my lifetime, or before I was born, but the atomic bomb. There was before the atomic bomb, and then in 1945, there's after the atomic bomb. It changed the world dramatically. Anywho, so a few more photos for people who care. The idea of this is, in our terminology, we've got a leaf spring. It's made of some kind of wood, and we make use of that elastic performance property of the wood. And, on it goes. This is early examples of beam and torsion springs. We've got this idea of twisted, you think of rope. You don't necessarily think of rope as a spring material, but pretty much every material has, in its elastic zone, you apply a force, you'll deflect that material a little bit, you release the force. So if the material returns back to its original length, it's behaved like a spring. And that's what the ancient Romans did with this device. They put some rocks or something nasty in the spoon bit, apply potential energy to that rope-based spring, twisted elastic rope, and then impulsively release it, and you'd get your object, flying over the wall of your enemy, and hopefully you win the day. But these days, that is a nice little side-on representation of a coil helical spring. We can have torsion springs in clocks. There's springs, hopefully everyone appreciates, in closed pegs. Hopefully everyone's thought about trucks, and the tray of a truck tends to not have a helical spring, but a leaf spring. And it's essentially just a series of beams that are providing, a resistance to load. So hopefully everyone can see there's that bit hooks in at the end, load from the vehicle there, load from the tray, and then these two arrows going up back into the main structure, down to the wheels. I can tell you that this spring in red is more likely to be compressive than the two springs on the top right, and it's got everything to do with having this effect here. Now, for the compression, of course, once we've compressed a little bit, we can have a cyclic compression in an automotive sense. But what's interesting, and we can be confident, depending on what the end effects is, we can have a constant spring rate. There is a bit of a difference between that and the top right, and if I can grab a pen, I'll... Cute. Just imagine you're starting to apply that load to the bottom one. I'll turn the light. This is just for a bit of fun. I'll turn the light on. Now, as one starts applying that load, deflection, force, is what I've just drawn up on the screen correct? And it's not, but can anyone say why it might not be correct? I'm looking at the coil spring at the top with the loop, and it could easily just as easily be that incomplete loop. Any thoughts? That's okay, I don't want to waste your time. That bit on the end, just contemplate. It's going to have to, it's going to have to absorb that load as well. And it's going to deflect a little bit as it absorbs the load as well. What we've essentially got here is what we've essentially got is 3 springs in series. The coil bit in the middle that we just think of as the spring, and we just think about this one as being a cantilever type spring. Just imagine fixed end there where it hits the main coil at both ends, cantilevering out, such that that cantilever effect is going to have to take up a bit of load, and it's going to, we can be pretty confident that we're going to have a K1 and a K1 and a K2. We could expect something like that there's going to be this little zone near the start of loading where those ends are going to have to take up the load. They'll deflect in a distinct way, and once that's sort of achieved, they've deflected to a saturation point, then the main spring will take the load. Now, for domestic, who cares type applications, it's not an issue. But it's important to make sure I got that right, because I've parallel. But if we're dealing with high performance, high speed, high tolerance type engineering, issues like that, now everyone in the room can never claim ignorance of issues like that. It's an important feature of being an engineer, to have that, the engineer's gaze. Now, I did spend a couple of seconds talking about the red, the automotive spring suspension. There it is in a spring damper assembly. There they are in just a rear suspension dependent linked system. That is, that the rear shaft, or the rear drive shaft, is one great big lump, so that what happens at this end of the shaft is going to have an impact down the other end. Spring is now independent from the damper, that is, the velocity dependent component of a spring damper system. There's a whole, and this is where it gets fun, with the Grand Prix just happening on Sunday, there's a whole, and hopefully some in the room are working with Melbourne University Racing at the moment, there's a whole heap of variations. And that's where it gets fun. It's this, here I've got the same spring every time, but with a heap of nice kinematics that tries to optimise something, whatever that something might be. And there is so much of it. It means that people have been workshopping this, trying to be creative about it a lot. And again, those who are into automotive design, something to think about. Every time it's the same spring. And I am aware that it doesn't have to be a coil spring. Formula type racing, I know that people have played around with essentially a pressurised vessel, like a hydraulic ram that will do all the spring effect. I don't know how well it's worked, but automotive tends to be coil springs because common as muck, reliability is good, nothing better really has come up, despite all these different variations. So, I did say leaf spring before, and there is an example of one with a photo. We've got the axle going to what's called the differential, where you can't see it all. The tyre, just a couple of D-clamps to a series of beams, essentially. A series of beams connected together, going out to this connection point, a pin joint, which is in this world is called a shackle, that provides this outcome. Now, again, if I've got time, I'd ask the class, but I'll just tell you, why is this a series of small, thin, plates of spring steel, and not just one great big chunk? Especially, why is it thicker down there than at the end there? Well, they've played around with the idea of if there's no load, not much mass being carried, well then you can have a gentler ride. You know, you don't need as much spring. As load increases, then the overall spring will start to deflect. The tray of the vehicle will start lowering to the ground, and more of the spring sections or beam sections come into play to help support the load. Now, I've got a nice little design. I don't know if you're getting it this year, but I actually have, I don't know if it's an exam question or if it's in a DP, actual investigation of this. So you may get it or you may not, I can't remember. But certainly this type of stuff is in Shigley type text where you can have a look at to go a bit deeper. It's 5.2. I'll quickly talk about this one. Here we've got another form of that same cantilever beam effect, and in this case it's trying to simulate the resistance to motion of the foot force down bottom right hand corner of that image for a by-wire braking system. That is, the human still wants to have some kind of resistance to motion to get the sense of doing something, of achieving an outcome, even though the human doesn't have to have that. And this kind of device can do that. Bottom left is the kind of coil spring that everyone who rides a bike and has a brake on that bike of the type you see there will be aware of. Again, it's coil, but the whole point of it is that it coils and resists motion, radially. It's analogous to a clothes peg, and I'll talk more about that in the lecture after Peter McGowan. So I'll stop for now and see you then.